What if I told you the most dangerous material on Earth is also the one holding up your entire life? Every bridge you cross, every apartment tower, every tunnel, dam, highway, and power plant. Concrete. It looks solid, permanent, silent, but inside it's always breaking. Cracks form within hours of being poured. Water seeps in. Steel rusts. Stress multiplies invisibly. And then, without warning, it fails. In 2007, a bridge in Minneapolis collapsed in seconds. In 2018, a highway bridge in Italy killed 43 people. In 2021, a beachfront tower in Florida fell while families slept. Different countries, different designs, same material. Now here's the part that sounds like science fiction, but isn't. Scientists have created concrete that heals itself. Not patched, not repaired. Healed. Cracks close automatically. Water is sealed out. Corrosion is stopped before it starts. Some versions use living bacteria that wake up decades later to rebuild stone from the inside. Others use artificial blood vessel networks that release healing agents exactly where damage appears. Some even copy an ancient trick the Romans figured out 2,000 years ago, and then somehow forgot. This isn't theoretical. It's already being poured into tunnels, highways, offshore wind farms, and nuclear facilities. And if it scales, it could quietly reshape $1 trillion of global infrastructure, slash carbon emissions, and redefine how long our civilization's foundations last. So why isn't everyone using it already? Why do most buildings still rely on a material we know is destined to crack? And why might the biggest obstacle to this breakthrough have nothing to do with science at all? That's where the real story begins. Right now. While you're watching this, millions of concrete structures across the world are aging toward failure. Not dramatically, not visibly, quietly. Concrete doesn't fail like glass. It fails like debt, slowly, invisibly, then all at once. Here's the scale most people never think about. Concrete is the second most consumed material on Earth after water. Over 30 billion tons are poured every year. Entire civilizations are quite literally resting on it. And much of that concrete was poured during massive construction booms in the 1950s, 60s, and 70s, which means a huge percentage of global infrastructure is now entering its failure acceleration phase. Bridges that were designed for 50 years are now 70 years old. Buildings meant to last a century are quietly bleeding strength from the inside. Tunnels, dams, and foundations are absorbing decades of stress, salt, freeze-thaw cycles, and corrosion. This isn't a future problem. It's a now problem. In the United States alone, engineers estimate trillions of dollars are needed just to keep existing infrastructure from collapsing into obsolescence. Globally, the number is far larger. And here's the brutal truth. We cannot afford to rebuild everything. Not financially, not logistically, not environmentally. Every time concrete fails, we don't just lose a structure, we burn carbon replacing it. Cement production alone accounts for roughly 8% of global CO2 emissions, more than the entire aviation industry. So every cracked bridge isn't just a safety risk, it's a climate liability. This is the trap modern civilization is stuck in, a material that enables growth, but demands endless repair, endless replacement, endless emissions. Unless the material itself changes, unless concrete stops behaving like something that slowly dies and starts behaving like something that responds. Self-healing concrete doesn't just promise stronger structures. It promises fewer disasters, lower taxes, lower emissions, and infrastructure that doesn't wait to fail before it's fixed. But to understand how radical that is, we need to go back, not forward, back nearly 2,000 years, to a civilization that accidentally solved this problem once already, and then somehow lost the knowledge. Walk through the ruins of ancient Rome, and you'll see something unsettling. The Pantheon's dome, still the largest unreinforced concrete dome on Earth, has stood for nearly 2,000 years. Roman harbors sit submerged in seawater, yet remain intact. Break a piece of Roman concrete open, and instead of crumbling, it looks denser than when it was first poured. This shouldn't be possible. Modern concrete is engineered to last 50 to 100 years. Roman concrete has lasted 20 times longer in harsher conditions, without steel reinforcement, without modern chemistry. For centuries, no one knew why. Historians assumed it was superior craftsmanship. Engineers blamed luck. Most modern builders simply ignored it because Roman concrete didn't fit industrial workflows. Then, in the last few decades, material scientists started looking closer, under microscopes, under X-rays, at the atomic level. And what they found changed everything. Roman concrete wasn't uniform. It was alive with chemistry. Embedded throughout the material were tiny white mineral inclusions, once dismissed as poor mixing. In reality, they were reactive lime clasts. When cracks formed, water seeped in. The lime reacted. New minerals crystallized inside the crack, sealing it shut. In other words, Roman concrete healed itself. Not perfectly, not instantly, but continuously over centuries. This wasn't intentional biotechnology. It was an accidental discovery born from volcanic ash, quicklime, and a construction process that created built-in chemical redundancy. And here's the uncomfortable part. Modern engineering optimized concrete for speed and cost, not longevity. We standardized it, smoothed out its imperfections, removed the very features that allowed it to adapt. In the process, we made concrete cheaper and far more fragile. Roman builders didn't know the science, but they understood something modern systems forgot. Durability isn't about resisting damage forever. It's about recovering from damage when it inevitably happens. That ancient insight is now colliding with modern science in a way the Romans could never have imagined, because today, self-healing concrete doesn't rely on accidents. It's engineered down to the microscopic scale. And the mechanisms scientists are using now are far more radical than lime and ash. To understand self-healing concrete, you have to let go of the idea that concrete is inert. It isn't. Concrete is a chemically active system that never fully stops reacting. Cracks don't mean it's dead. They mean stress has found a path. Self-healing concrete works by turning that weakness into a trigger. The most widely studied approach uses something that sounds almost absurd: bacteria. Specifically, dormant spores of bacteria that can survive for decades without food, oxygen, or light. Scientists embed these spores inside microscopic capsules mixed into fresh concrete. Alongside them, nutrients, often calcium lactate. When the concrete is intact, nothing happens. But when a crack forms, water enters. That water wakes the bacteria. They metabolize the nutrients and produce calcium carbonate, the same mineral found in limestone and seashells. The result? The crack fills itself with new stone. No sensors, no electronics, no human intervention. Just chemistry responding to damage. Other approaches skip biology and go fully synthetic. Some use polymer microcapsules that rupture when cracks propagate, releasing liquid healing agents that solidify on contact with air or moisture. Others use vascular networks, tiny engineered channels that act like artificial blood vessels, delivering repair compounds precisely where they're needed. In all cases, the principle is the same. Damage isn't the end state. It's the signal. And here's what makes this revolutionary. Traditional concrete maintenance is reactive. You wait for visible damage. Then you patch. Self-healing concrete is proactive at the material level. It intervenes before cracks grow large enough to weaken steel reinforcement, allow corrosion, or trigger cascading failure. Think of it less like stronger concrete and more like concrete with an immune system. But this first generation of self-healing materials has limits. They work best on small cracks. They cost more. And scaling them to millions of tons of infrastructure introduces challenges no lab test can fully simulate, which leads to the next twist in the story. Because the most promising breakthroughs aren't coming from adding more complexity. They're coming from making concrete simpler. And the solution might already exist inside the concrete we pour today. Here's the twist that caught even material scientists off guard. Some of the most promising self-healing concrete doesn't rely on bacteria, polymers, or futuristic networks. It relies on doing something almost embarrassingly simple, not over-optimizing concrete. For decades, modern concrete production chased uniformity, perfect mixing, perfect consistency, perfect predictability. But in chasing perfection, engineers accidentally erase concrete's ability to respond. Recent research showed that when concrete is produced using hot mix quicklime, a method similar to Roman techniques, it naturally forms reactive lime inclusions. Those inclusions act like built-in repair kits. When a crack forms and water enters, the lime dissolves, migrates into crack, and recrystallizes, sealing it shut. No added capsules, no living organisms, no complex manufacturing changes, just chemistry that wants to reach equilibrium. Even more surprising, these inclusions also make cracks more visible and more likely to intersect healing zones, meaning the material guides damage toward repair pathways. It's not smarter technology. It's humble engineering. And this approach solves several problems at once. Lower cost, higher compatibility with existing concrete plants, better long-term reliability. In pilot projects, concretes designed this way show dramatically reduced water permeability and longer structural life, without any exotic additives. The implication is unsettling. We didn't need to invent a miracle material. We needed to stop stripping away resilience in materials we already had. But this raises a new question. If self-healing concrete can be cheaper, simpler, and longer lasting, why isn't it everywhere? Why are most bridges, buildings, and roads still poured with materials we know will fail? The answer has very little to do with science, and everything to do with how modern systems decide what gets built. On paper, self-healing concrete looks like a solved problem. Multiple working mechanisms, repeatable lab results, decades of research, and yet adoption is painfully slow. The reason is a gap that kills more innovations than bad science ever could. The scale gap. Concrete isn't like electronics or software. You don't update it. You don't patch it later. Once it's poured, it's locked in for 50, 100, sometimes 150 years. That makes every change terrifying. Infrastructure projects are designed around risk minimization, not innovation. Engineers are legally responsible for failures that may happen decades after they retire. Contractors are paid to deliver on time and on budget, not to experiment. So even if a new concrete is better, if it's unfamiliar, it's risky. Then there's testing. To certify a new concrete mix, regulators demand performance data across freeze-thaw cycles, salt exposure, seismic stress, and decades of simulated aging. That testing can take years. And self-healing behavior adds a paradox. You have to let the concrete crack to prove it heals. That's hard to standardize. Cost is another friction point. Even a 10 to 20% price increase per cubic meter can kill adoption when projects involve millions of tons of material. Decision makers often ask a short-sighted question. Why pay more now for damage that hasn't happened yet? That logic works. Until it doesn't. Because once failure begins, repair costs explode, which is why the most interesting progress isn't happening in highways or office buildings. It's happening in places where failure is not an option, where repair is impossible, where longevity is worth any upfront cost. And in those extreme environments, self-healing concrete isn't a luxury. It's a necessity. If a sidewalk cracks, it's an inconvenience. If a bridge cracks, it's a crisis. But there are places where concrete failure is something far worse. Places where repair is impossible, where access is limited, where mistakes don't just cost money, they risk catastrophe. That's where self-healing concrete quietly moved from theory to reality. One of the earliest real-world adopters wasn't city. It was the energy sector. Offshore wind turbines rely on massive concrete foundations, constantly battered by waves, salt water, and cyclic loading. Sending repair crews is expensive, dangerous, and sometimes impossible. Self-healing concrete offered something traditional materials couldn't, a chance to never need those repairs. Similar logic drove adoption in underground tunnels and wastewater infrastructure, where cracks mean leaks, contamination, and long-term structural decay. In these environments, bacteria-based healing systems proved especially effective. The bacteria don't care about darkness. They don't care about pressure. They don't care about decades of silence. They wait, and when water finds a crack, they respond. But the most striking example comes from nuclear containment structures. Here, microcracks are unacceptable. Even tiny leaks can escalate into long-term risk. Self-healing concretes are being studied and deployed to seal microfractures before they can ever propagate. No press releases, no hype, just quiet material decisions made by engineers who understand one thing deeply. Prevention is always cheaper than regret. These early adopters aren't chasing innovation for its own sake. They're chasing certainty. And once materials prove themselves in the harshest conditions imaginable, they don't stay niche for long, which leads to the next cascade. Because if concrete can heal itself in offshore storms and radioactive environments, what happens when that same logic is applied everywhere else? Once self-healing, concrete works in the most extreme environments. Something inevitable happens. It spreads, not all at once, not everywhere, but in a cascade, starting where it saves the most pain. Roads and highways are an obvious next step. Microcracks form within months of heavy traffic. Water enters. Freeze-thaw cycles tear them open. Self-healing concrete changes that dynamic. Cracks seal before water penetrates. Salt stays out. Rebar stays protected. That alone can double a road service life. In cities, buildings benefit differently. Foundations experience slow, uneven settlement. Tiny cracks form, not enough to trigger alarms, but enough to weaken structures over decades. Self-healing materials arrest that damage early. In coastal regions, where saltwater corrosion eats concrete from the inside out, healing mechanisms act as constant defense. Then there's a quieter, less obvious application. Water infrastructure, pipes, reservoirs, treatment plants. Leaks don't just waste water. They destabilize surrounding soil and undermine entire systems. Concrete that seals itself reduces loss, contamination, and collapse risk simultaneously. And perhaps the most profound shift is economic. Instead of budgeting for endless inspection, repair, and replacement cycles, cities can budget for longevity. That changes how infrastructure is planned, how taxes are allocated, how risk is priced. But there's an even larger implication hiding beneath all of this, because concrete isn't just a material, it's a template. If we can teach the most widely used material on Earth to respond to damage, what does that mean for every other material we depend on? Polymers, metals, composites. Self-healing concrete isn't the end of the story. It's the opening chapter of a new design philosophy, one where materials aren't passive. They participate. Self-healing concrete sounds like an obvious upgrade, but engineers are trained to distrust anything that behaves unpredictably, because healing is not the same as control. Most self-healing systems are designed to repair microcracks, not major structural damage. They're preventative, not miraculous. If a bridge column fractures under overload, bacteria won't save it. If a foundation shifts beyond its design limits, chemistry can't rewrite physics. That distinction matters, because hype blurs it. Another concern is time. Healing doesn't always happen instantly. Some systems take days or weeks to fully seal cracks. In certain structures, that delay could still allow corrosion or leakage. Then there's durability of the healing mechanism itself. Bacteria can exhaust their nutrients. Microcapsules can rupture only once. Chemical reactions can run out of reactive material. After enough damage cycles, the concrete may stop responding, which raises a deeply uncomfortable question for engineers. How do you certify something that changes over time? Traditional materials are static. You test them, rate them, and assume they behave the same way forever. Self-healing materials are dynamic. They age. They react. They adapt. That breaks existing standards. And standards aren't just bureaucracy. They're safety nets built on hard-earned failures. There's also the question of unintended consequences. What if healing seals cracks that engineers need to see? What if it masks warning signs of deeper structural issues? What if reliance on self-healing encourages riskier design margins? These aren't abstract concerns. They're the reason adoption is cautious, incremental, and heavily scrutinized. But tension doesn't stop progress. It refines it. And right now, researchers are doing something critical. They're redesigning self-healing concrete, not as a replacement for inspection, but as a partner to it. And that shift, from autonomy to collaboration, is unlocking the next breakthrough. Here's the quiet shift happening behind the scenes. The future of self-healing concrete isn't autonomous. It's instrumented. The most advanced research no longer treats concrete as a passive block that magically fixes itself. It treats it as a system, one that senses, reports, and responds. Instead of hiding damage, next-generation self-healing concrete is designed to expose it intelligently. Fiber optic strands embedded inside the structure detect microscopic strain, changes long before visible cracks form. Electrical resistance measurements track internal fracture growth in real time. Acoustic signals capture the sound of cracking as it happens. The concrete doesn't just heal, it alerts. When a crack forms, the system knows where it is, how fast it's growing, whether healing succeeded, whether intervention is required. Healing becomes conditional, not blind. If the crack is small, passive healing activates. If the crack persists, monitoring escalates. If the crack grows, engineers are notified before failure cascades. This changes everything, because now self-healing concrete isn't hiding risk. It's compressing response time. Failures like Champlain Towers didn't happen because damage was invisible. They happened because damage was slow, cumulative, and ignored. Self-healing systems flip that equation. They slow deterioration and make it impossible to miss. This is why regulators are starting to soften, not because the concrete is smarter, but because the oversight is. In testing, structures equipped with sensing plus healing show earlier intervention windows, fewer emergency repairs, dramatically reduce inspection uncertainty. The material isn't replacing engineers, it's extending them. And once concrete becomes something you can continuously interrogate, not just inspect every 5 years, the economic math starts to break. Because now maintenance becomes predictive instead of reactive, and that's when costs collapse. For decades, better concrete existed. And for decades, almost no one paid extra for it. Because construction doesn't reward longevity. It rewards lowest upfront cost. That's the paradox self-healing concrete had to break. And it's finally breaking it. Not because engineers changed, but because money did. Here's the shift. Infrastructure is no longer priced as a one-time asset. It's being priced as a risk-adjusted, long-duration liability. Insurance companies now model climate stress, corrosion risk, and failure probability across decades. Pension funds hold bridges, tunnels, and utilities for 30 to 70 years. Governments are issuing infrastructure bonds tied performance metrics, not just construction cost. In that world, concrete that quietly degrades is a financial threat. Self-healing concrete does two things investors care deeply about. It extends asset life. It reduces uncertainty. And uncertainty is what destroys long-term returns. When a bridge has embedded monitoring and autonomous crack repair, its risk profile changes. Lower failure probability means lower insurance premiums, lower maintenance reserves, higher bond ratings, cheaper financing. A 20 to 40% increase in material costs becomes irrelevant if it cuts lifetime risk in half. This is why patient capital is moving in. Climate-focused funds, sovereign wealth funds, and infrastructure investors don't need 5-year exits. They need predictability. Self-healing concrete offers something rare in infrastructure, a way to lock in durability upfront. That's also why major incumbents, cement giants, insurers, and reinsurance firms are now involved, not because it's futuristic, because it's actuarially attractive. And once insurers start pricing structures differently based on material intelligence, adoption stops being optional. It becomes financial gravity. If self-healing concrete makes so much sense, why isn't it everywhere already? Because construction isn't just an industry. It's a legal, cultural, and procedural ecosystem built to avoid blame. Innovation isn't rewarded. Familiarity is. Every bridge, tunnel, or building is signed off by licensed engineers whose careers depend on one thing: nothing going wrong. Using a new material, even a better one, creates liability asymmetry. If standard concrete fails, the failure is unfortunate. If novel concrete fails, it's negligence. That fear alone slows adoption by years. Then there are codes. Most building codes don't describe performance. They describe recipes, exact cement ratios, specified admixtures, approved methods. Self-healing concrete doesn't fit neatly into that framework. It behaves correctly, but not traditionally. Changing codes requires years of field data, multiple standards bodies, conservative consensus. That's a 10 to 20-year cycle. Next is fragmentation. Construction isn't dominated by a few players. It's millions of contractors, suppliers, inspectors, and municipalities, each with their own incentives. No single actor captures the full benefit of durability. The builder wants speed. The developer wants lower cost. The owner wants longevity. The city wants safety. Self-healing concrete benefits the last two, but is paid for by the first two. That misalignment stalls everything. And finally, training. New materials mean new mixing protocols, new curing requirements, new inspection standards. That demands retraining, an enormous global workforce. This is why adoption isn't explosive. It's selective. Self-healing concrete shows up first where failure is unacceptable. Access for repair is difficult. Lifespan is mission critical. Tunnels, nuclear facilities, offshore wind foundations, water infrastructure, not parking garages, not sidewalks. Yet, but this bottleneck isn't permanent because the pressure isn't coming from builders. It's coming from regulators, insurers, and asset owners. And once those three align, adoption accelerates very fast. Here's the honest answer most videos avoid. Self-healing concrete will not suddenly replace traditional concrete. It will outlive it. Construction doesn't change in revolutions. It changes in generations. Right now, self-healing concrete is exactly where renewable energy was in the early 2000s. Technically proven, economically logical over time, politically supported in pieces, still treated as experimental. So what does the real timeline look like? Phase 1, 2025 to 2030, proof under pressure. This is the validation era. Governments quietly deploy self-healing systems in bridges with no redundancy, tunnels under dense cities, water systems where leaks are catastrophic. Insurance companies begin tracking loss reduction. Regulators begin writing performance-based clauses instead of prescriptive ones. Nothing looks dramatic yet, but the data pile grows. Phase 2, 2030 to 2040, mandated durability. This is the inflection point. Carbon pricing, embodied carbon limits, and maintenance liabilities converge. If a structure can last twice as long using the same raw materials, regulators start asking, why didn't you? At this stage, self-healing additives are written into infrastructure specs. Public projects require life cycle cost justification. Insurers discount premiums for durable materials. Cost premiums shrink through scale. Engineers stop asking if it works and start asking which system to use. Phase 3, 2040 to 2050, the invisible standard. By now, most concrete quietly heals itself. No branding, no headlines, no novelty, just fewer cracks, fewer inspections, fewer failures. The technology disappears into normalcy. That's how real infrastructure change happens, not as a miracle, as a default. And here's the part that matters most. Once durability becomes regulated, non-healing concrete becomes a risky option. That flips the entire market. At that moment, adoption doesn't spread because it's innovative. It spreads because not using it becomes indefensible. And when that happens, the trillion-dollar number stops sounding ambitious. It starts sounding conservative. Self-healing concrete isn't really about concrete. It's about time. Every crack that seals itself delays decay. Every structure that lasts longer delays replacement. Every replacement we avoid delays emissions, disruption, and disaster. That's the hidden leverage. Concrete doesn't fail loudly at first. It fails quietly, over decades, until suddenly it doesn't. Self-healing materials interrupt that curve. They flatten the slow decay phase and postpone the cliff. And that changes everything downstream. Cities stop budgeting for constant repair. Governments stop choosing between safety and affordability. Engineers design for lifetimes, not inspection cycles. But zoom out further. Concrete is the physical backbone of housing, transportation, energy, water, defense. When that backbone becomes self-repairing, society becomes more resilient without having to move faster, work harder, or build more. That's rare. Most climate solutions ask us to sacrifice. This one asks us to waste less. And there's a deeper shift happening. For centuries, our materials were passive. They obeyed physics, and that was it. Self-healing concrete is different. It senses damage. It responds. It adapts. That's not a new material category. That's a new philosophy of infrastructure. One where failure isn't surprise. It's an input. And once we accept that idea, it doesn't stop at concrete. It spreads to self-healing metals, adaptive grids, autonomous maintenance systems, infrastructure that doesn't just stand there, but participates in its own survival. So, when people ask, is this really worth $1 trillion? They're asking the wrong question. The right one is, what is stability worth in an unstable world? Because the most valuable technologies of the future won't be the fastest. They'll be the ones that quietly prevent catastrophe. And those rarely make headlines until the day they save us. That's the story of self-healing concrete, not as a miracle, but as a turning point.